Hello everyone, my name is Salah Farouki. I am the lead R&D scientist here at Petrolern. Today I will be hosting this session. Let's wait for a few more minutes so other folks can join us. Thank you. I think we can go ahead and get started. Hello again everyone, my name is Salah and I am the lead R&D scientist at Petrolern. I welcome you to the sixth talk from Petrolern at Home seminar series. Today I am pleased to introduce our expert speaker, Dr. Hamid Soroush. As you know, we are experiencing a very difficult time with both COVID-19 and low oil prices. The objective of this seminar series is to keep people learning and motivated. Specifically, we are planning many talks on geothermal and carbon storage subsurface application to show oil and gas people that there are many opportunities out there for you. I hope that we all pass through this time safely. I would like to thank all industry experts who accepted to give a talk here. We are working on the June schedule right now. In case, if in case you are interested to give a talk, please contact me via email at info@petrolern.com. Our next seminar is on Friday, May 1st, a very interesting talk by Richard Esposito titled An Overview of the Southwest Regional Carbon Sequestration Partnership. At this point, I would like to ask everyone to mute the microphone and turn off cameras. If you have any question, please type them in a public chat section. Just make sure you send them to everyone. If for any technical and non-technical reason you could not stay with us till the end of the presentation, don't worry, we will record all the talks and we will post them on our website. Now I am going to introduce our speaker today. Dr. Soroush is an internationally recognized geomechanics expert with 25 years of experience in geomechanics application, oil and gas, geothermal, and CO2 sequestration. He has conducted or managed more than 200 consulting and research projects worldwide. Hamid is currently the CEO of the Petrolern LLC, providing strategic planning, project management, and technical leadership. Prior to that, he held positions with various companies such as Dong, Shell, Weatherford, Synergy, GMI, and several more companies in different locations around the world. His current technical focus is on sustainable development of unconventional resources and geothermal energy with advanced geomechanical analysis. Hamid holds a Bachelor of Engineering in Mining Engineering, Master in Rock Mechanics, and PhD in Petroleum Engineering from Curtin University of Technology in Australia. He has published 3 technical books and many journals and conference papers. Hamid has given different industry courses for Petrolern, SPE, and EAGE, and has been selected 3 times as SPE Distinguished Lecturer for the 2012, 2017, and 2020 seasons. His presentation title today is The Cost-Saving Role of Geomechanics in Oil and Gas Industry. With that, I would like to turn it to Hamid to start the presentation.
Yeah, thank you, Salah. Hello, everyone, and thanks for your time joining my talk today. I see about 60 people in the meeting from all over the world, and there are more people actually joining. Since I'm actually the host, so I might I have to watch on the waiting room to see who is coming in. So if you see interruption in my talk, so I'm just trying to admit everybody requesting for joining the meeting. So as you know, I'm going to talk about geomechanics and specifically its importance and role in harsh, economic basically environments like the environment we are in right now. As you know, geomechanics has been actually introduced to the oil and gas industry several decades ago. I would say the revolution in the geomechanics application in oil and gas goes back to early 2000, and since then, different people are applying actually geomechanics to different applications like drilling, reservoir engineering, completion design, hydraulic fracturing, stimulation. But the fact is that still many companies, many operators look at geomechanics as a luxury service. It means that if they have extra money, if they have good economic condition, they might request for that. Otherwise, is the first thing they cut from the budget, and is a mistake. My whole idea today is to basically explain how geomechanics is going to save time, money, and increase safety for different oil and gas operations, specifically in this harsh economic condition. And this is the condition that companies should be smart and use technologies and knowledge like geomechanics to basically reduce their costs rather than laying off people and losing their smart resources. So there are always other, smarter ways to basically reduce the cost and basically run the company in an economic level. So for people who are in the geomechanics business, this presentation is not really advanced geomechanics presentation, is more practical. And I made it very simple and operational for people from different backgrounds to be able to understand and take advantage of it. So I'm going to actually start with a quick introduction to geomechanics and its importance and the overall application of it. And then I'm going to focus on two different, basically, the discipline within geomechanics. One, drilling applications, and the other one, production applications. And through this, basically, two sections, I'm going to give you some of the outputs and some of the case examples or case studies that geomechanics basically could help operators to save a lot of money and time actually on their operations. And at the end, I'm actually open for to take questions. So as you know, rock mechanics is basically the theoretical and applied science of mechanical behavior of the rocks or response of the rock to the field of stress and forces around it. So basically we have rock, and on this rock there are stresses, forces, fluid pressure acting, and rock mechanics science basically help us to predict the rock behavior under this stress or force environment. You might ask, what was then geomechanics? Is there any difference between geomechanics and rock mechanics? The answer is that in a broader term, geomechanics is a science of predicting or modeling rock geomaterial science, basic geomaterials behavior under a stress field. So rock mechanics is focused on rock. Geomechanics is basically include also soil or any other material that you might imagine is in the earth, right? But in terms of oil and gas industry, when we use geomechanics, because we are mainly dealing with rock, not soil, so geomechanics is basically equivalent to rock mechanics. So you might interchangeably use these two terms when you are using basically the science. So the term petroleum geomechanics is basically the science of geomechanics applied to the oil and gas applications. And it actually has a big flavor of geophysical, petrophysical, and geological knowledge and science combined with rock mechanics to basically quantify the response of the earth to changes in, for example, stresses, reservoir pressure, formation temperature, any basically physical or mechanical changes that naturally apply to the formations, or we apply to the formation by basically our operations like drilling or production or so on. So the role of geomechanics, you know that all of us, regardless of our background or our job title or what we are doing, either, I mean, we are a manager or we are a technical person, we are a reservoir engineer or drilling engineer, we all have three important objectives: to reduce non-productive time, to cut the costs, and to minimize the risk to have a safer working environment. And geomechanics is a perfect example of a tool which can provide these three objectives. And through this presentation, I'm going to actually explain a little bit more how geomechanics can basically contribute in these three main objectives. So the question is how much geomechanics can basically save for oil and gas industry. There are many statistics out there. There are some publications showing that, I mean, for specific projects or cases, how much geomechanics could basically help operators. But one of the most documented and comprehensive paper out there is from Dodson and Dodson in 2004. And what Dodson did, they review all the public data from the wells in the Gulf of Mexico only. And they looked at the daily drilling reports and extracted all the problems that caused non-productive time during drilling. And based on their study, they noticed that 67% of non-productive time during drilling in the Gulf of Mexico was due to wellbore stability issues. These issues are either related to the formation collapsing or getting kicks, pore pressure problem, or basically losing the mud into the formation. So other problems which are non-related to geomechanics or wellbore stability, they can be like waiting on weather, mechanical problems, you know, any reason that's basically logistic reason or operational issue that stopped drilling. And based on this study, the cost of wellbore stability problems only for basically the Gulf of Mexico operators annually is about $8 billion US. It is huge amount of money. I mean, you know how big is this number. What I did here differently, I went through this data and I tried to classify this data to basically, as you see the color codes here on the basically graph on the left, the red colors are problems which are related to the formation collapse or rock collapse. Is basically when all the problems that come with the formation getting fail in shear or basically cuttings that come to the wellbore, extra cutting cavings that create problems like the stock pipe, twist off, chemical instability in shale is part of the basically formation collapse, and so on, right? The green color problems are related to fracking into the formation or reopening basically existing fractures and losing the mud, right? Problems like loss circulation, mud losses, cement squeeze, or using LCM. These type of basically the keywords in the drilling reports show that there was some kind of problem with the fracturing into the formation. And then blue colors here are related to the pore pressure. So when we see kicks, blowouts, shallow water, gas flow, they all kind of indicate that pore pressure is kind of higher than the mud weight that we are using. So then on the plot on the right, what I did, I actually found the portion of each set of problems. And as you can see, about 35% of the problems are related to pore pressure. So it means, mud weight is not suitable to basically keep the pore pressure from flowing, from basically kicking the well. 34% is related to the fracturing. It means we unintentionally fracking the formation or opening natural fractures. And 30% roughly is related to the collapse of the formation. So just want to show that equally these three sets of problems are important to drilling and to basically minimize this non-productive time during drilling. Just to overally and briefly review different application of geomechanics, I took this beautiful schematic from Schlumberger website. So as you see, before drilling, pore pressure prediction is a part of geomechanical, the full, geomechanical study basically process. That we need to know when we drill into a formation how the pressure inside the formation, the fluid pressure inside the formation are changing. So then we can be ready basically to combat with that, right? When we drill, of course, wellbore stability issues and predicting them and try to mitigate them is one of the major basically application of geomechanics in drilling. With geomechanics, we can optimize not only the mud weight, but the casing design to basically have a smoother drilling and less basically problems. Again, we need to be ready for the areas or formations that there's risk of getting the mud lost. When we go to the reservoir, basically, if we need to do a stimulation in tight formation, again, geomechanics can contribute into that. If we are talking about reservoirs which are fractured and we want to see the effect, basically the behavior of these fractures when we inject to the reservoir during an EOR basically process, or if we produce and deplete the reservoir, what's going to happen to these fractures and faults? Are they going to be reactivated or not? Is another application of geomechanics. Then during production, if you are in the sand, which has potential to basically fail during production and create sand production, again, geomechanics can help to predict and kind of evaluate the amount of sanding during the production time. And the compaction of the reservoir due to production is another long-term basically application of geomechanics. And at the end, actually, we have to take care of the subsurface subsidence, right? How much of this compaction, basically deformation, can be transferred to the surface. So as you see, the application of geomechanics in oil and gas industry can be from well scale to whole field scale, and from very early stage of exploration and appraisal, all the way to even after abandonment when we are dealing with the subsidence. So the first thing I want to actually mention here is that it is a very, very big mistake to wait until a problem happens during drilling and then start thinking about geomechanics. Geomechanics has to be applied from the time we are planning for exploration, we are putting together our development plan, and all the way during the development and even after abandonment. So what is the geomechanical model? What is the base for basically studies in different applications, right? What do we need to have to be able to do all these applications and take benefit of geomechanics? So this slide shows simply components of a geomechanical model. So apart from the geological model and reservoir engineering, basically parameters that goes to the geomechanical model as input, the main components of a geomechanical model are these 6 components that I'm showing here. There are 3 principal stresses, which are usually, they're not always, but they're usually vertical stress, and 2 horizontal stresses that we call the minimum horizontal stress and maximum horizontal stress. And these stresses, they have, and these are perpendicular, basically, stresses, parameters. So these stresses, they have an orientation, which we usually show it with the azimuth of the maximum horizontal stress. And having this azimuth, basically, we will have all 3 principal stresses orientation. Then we have formation with fluid in it, and this fluid has a pressure, so we call it pore pressure. In some formations, this pore pressure is just weight of the basically the height of the head of the fluid, which we call it a normal pore pressure regime. And in some formation, specifically tight formation, these are can be actually overpressured. So we call them abnormal pressure, basically, formations. And then these formations have mechanical properties, right? So I put it as a one component here, but rock properties are several. So we might look at the elastic properties of the rock, like Young's modulus, Poisson ratio, shear modulus, bulk modulus, or strength parameters of the rock, like cohesion, friction, angle, UCS of the rock. So all these parameters basically go to the rock property model. And these are the parameters that define that if we change the stresses, any of these stresses or pore pressure, how the rock or formation will basically react to it. So how a geomechanical model look like on paper? This is basically what we call it a 1D geomechanical model. As you see, we have the pore pressure, we have minimum and maximum horizontal stress and normal or overburden stress, vertical stress. There are different terms for that. And then rock property is basically concluded in this line here, is a red line. I will explain later on what it is. And as you see, we have like 5 components of the components that I just talked about it. The one that we are missing is the stress orientation. We can just put it up there, right? Now, if we are looking at the field in 3D, basically geometry, then to create a 3D geomechanical earth model, first of all, we need to have a structural geological model, which usually comes from geology. Then we need a numerical model. It can be either finite element model or discrete element model or boundary element model, but all the geomechanical properties are basically in this numerical model, rock properties and stresses and pore pressure. And then at the end of the day, we need to have a reservoir model to be basically coupled with these 2 models to create what we call it a coupled geomechanical model. So now what you can do, you can basically change the rock properties here in the numerical model and see the effect of it on the fault and fractures, see the effect on the reservoir performance, you can basically reduce the pore pressure, like what we do during production, and see how the porosity permeability of the reservoir will change. Or you can change the reservoir parameters and see the effect on stresses and rock property, and again, fault. So it's basically a kind of link type of triple models that you can play with it and kind of predict the reservoir or production performance during the life of the field, right? So the good thing about 3D geomechanical model is that during production and change in the stresses and basically pore pressure, you can analyze the reactivation of the fault and fractures. You can look at the stress orientation to see how if they change or not, and what are the changes in different basic segments of the reservoir. And you can even extract 1D geomechanical models for the planned wells in different part of the field, and it will give you the wellbore stability model. The biggest challenge with 3D geomechanical model is the resolution, which sometimes, I mean, due to large size of the model, we cannot really go to the grid size that we need for some of our analysis. So we cannot, I mean, the best application of geomechanics is just look at the reservoir applications, not the well applications. So for wellbore stability, I always prefer to use 1D geomechanical model. So this slide is quite important because what we call it a stress regime basically defines how our well, our drilling operation, our reservoir performance will be during the operations, right? So the relative magnitude of those 3 principal stresses shows that which stress regime we are in. If the vertical stress is the biggest stress, and then the 2, of course, horizontal stresses are smaller, we are in normal stress regime or normal faulting regime in geological term, right? So in this case, all the active faults in the area are probably normal faults. If the maximum horizontal stress is bigger than the vertical stress, but SH mean is still smaller than vertical stress, we are in a stochastic regime, right? So the faults we expect to be stochastic faults, right? Like San Andreas in California in the US, what you see on the right. And the last stress regime is when both horizontal stresses are larger than vertical stress. So we are in reverse or truss stress regime, right? So geologists usually call it compressional stress regime, and normal, they call it extensional. But in geomechanics, we stick to this normal, stochastic, and reverse stress regime, basic terminology. So if you drill a well with a given trajectory, a given mud weight, a given casing design, but drill it in the 3 different stress regime, you will see totally different reaction of the rock formation to your operation. So this is very important to know which stress regime we are operating in. So let's move to the applications. I would like to start with drilling, which is basically one of the most popular or common type of applications of geomechanics. What is wellbore stability? So as I mentioned before, part of wellbore stability goes back to the pore pressure. And the fact that if our mud weight is basically enough or sufficient to basically keep the formation, the fluid inside the formation and stop it from flowing into the well and creating problems like kicks, blowouts, inflows. These are problems that really scare people on the rig, and they don't really want to see kicks and stuff. So, so this is part of wellbore stability. The second part of wellbore stability relates to the very low mud weight or basically drilling fluid pressure, which cannot keep the formation stable. Specifically, if formations are weak, like very naturally fractured rock, like in carbonates, or unconsolidated, semi-consolidated sandstone, like brittle shale, or shales which are very reactive to basically to water, or salt, which is a very plastic and squeezing material, swelling shale. These are the type of formation that needs support from mud, basically to mud pressures to be able to stay stable during the drilling, right? So we have to design the mud to basically stop this type of problem. And the last part of the wellbore stability problem is related to using too high mud weight or mud pressure, somehow that we either frag the formation and then get the mud lost into the formation, or even, you know, reopening existing fractures that can be either tensile fractures or shear fractures that already created due to geological, basically, conditions. So we might just use a mud weight that reopen them and get the mud lost. So all these problems are time consuming. They are risk to the projects. They have safety issues, and they are costly to remove them, right? Any of this problem, if you want to remove them or mitigate them, we have to spend actually a lot of time and money during the drilling. So this is a slide. I would like to actually discuss what we call it safe operating mud weight window for drillers, right? Classically or traditionally, drillers think that if they drill with a mud weight in between pore pressure and fracture gradient, we are safe because we don't get kicks, blowouts, and we don't get losses. So everything is okay. But honestly, it is one of the biggest mistakes that drillers do, or people who provide this type of basically information to them. Because there is another important line here, which we call it collapse gradient or shear failure gradient. And this line is related to the formation, right? Collapse gradient is the minimum mud weight required to keep a formation stable, right? So it doesn't collapse, it doesn't create problems like bit getting stuck or tools getting stuck in the well. Creating extra caving cuttings basically to create a cleaning problem in the well. So if we drill with a mud weight here, so without having this line, we are safe, but it's just because we are lucky, right? How if we drill with a mud weight here, right? We don't get kicks, we don't get losses, but we get severe formation collapse or formation, which basically result in losing the well sometimes, right? So it's not really safe to just calculate frac gradient and pore pressure and give it to drillers and say, okay, just design your mud weight in between and do your job, right? It's a big mistake. So, but not all of the formation have this red line or collapse gradient this high, right? Some formation are strong enough to basically support themselves. So this collapse gradient can be actually below the pore pressure. And this is the only case that we are able to drill with a mud weight with pressure below pore pressure. We call it underbalanced drilling. And underbalanced drilling has many actually advantages over overbalanced drilling. Some of them includes like specifically in the reservoir, when you use underbalance, you minimize the damage or even remove the damage to the reservoir. Underbalanced drilling is much faster, so you save on time quite a lot because you are drilling in a very low pressure environment. In the context of unconventional resources, when we basically drill into very tight formation, and specifically when we are in exploration or appraisal phase, underbalance drilling is the only technology that you can basically produce while you're drilling, right? What does it mean? It means that if you're looking for shale or a tight sand, for example, which include gas and oil, and you use overbalance, basically it's really, really hard or kind of impossible to detect the reservoir, right? So this is why shale producers or explorers, they really like to do underbalance in order to be able to find the tight resources. So in some formations, like very weak formations or heavily fractured formations, the fracture gradient is quite low and the collapse gradient is quite high because rock is very weak and it needs support to basically keep it stable. So as you see in these cases, the mud weight window is very, very narrow, and it's really hard to keep the mud weight in between these two limits, right? So in these cases, technologies like managed pressure drilling or controlled pressure drilling come to help us to be able to actually drill, right? So as you see, the higher boundary of the mud weight window is the green line here, is frac gradient, but the lower boundary of the window is either pore pressure or collapse gradient, whichever is larger. So we need to have both of them to be able to actually optimize the mud design. And even as you see, geomechanics here, and this red line is the biggest contribution of geomechanics to mud weight window. Although geomechanics help with basically getting better frac gradient and sometimes help pore pressure basically people to calibrate and refine their pore pressure model. But this red line here is, I would say, the biggest contribution of geomechanics to mud-wet window. So as you see, this line even helps us to find the technology, to optimize the technology that we should use for drilling, right? Like if you are in the HPHT field, probably you are in such a situation, although your rocks might be not very weak, but usually the window is very weak, very narrow, and you might need to actually use MPD. So this is an example of a 1D geomechanical model. Is a typical North Sea. Basically, this one is from Danish North Sea. As you see, again, we have the pore pressure, we have the collapse gradient here, red line. We have the formation, basically fracture gradient, and this is the vertical stress. But for wellbore stability, all we need is this line, the red line, and the pore pressure. And as you see in part of the basically well trajectory, collapse gradient is controlling the mud-wet window, this green area. But in some other parts, like here, pore pressure becomes actually the main player. And of course, frac gradient always on the other side. So all these parameters has to be calibrated actually using some data that we need to acquire during drilling the offset wells. So after drilling the well, if we look at the actual mud weight and ECD and the drilling problems that we got during drilling incidents, we are able to further calibrate and update our model. For example, in this section here, you see that the ECD is actually passing the frac gradient. So it means we should see some sign of, either ballooning or losses. If we didn't see that, it means our model is not really correct here. We have to fix the model. If we saw that, it's kind of validating the model. Or for example, here, you see the static mud weight went below the collapse gradient. So it means that during drilling, we should have noticed either like tight holes problem or noticing some extra cuttings and cavings. So these are the type of calibration that are needed actually to do after drilling the well. So now I'm going to give you a few examples how geomechanics basically save money for our clients during some of the project that we previously did. This example is from an old case in Northwest Shelf, Australia. We did this project, I think, in early 2000. So this plot here is a typical depth versus time plot that drillers use to basically plan their drilling program. And this black line is what they call it planned, basically drilling, the plan for the drilling, which shows in each day of drilling how many basically meters or feet they're going to drill, when they're going to stop basically to put the casing, and so on. And usually, typically, after drilling, if you plot this data again, you will see something very different. There are always delays in the project, there are non-productive time, and so on. But in this case, the delay was about, if you look at the days, it's about 50 days delay in the project and compare with the plan. And at the end of the day, they never reached the target, right? And as you can see, they face different type of problems. They got like tools stock or bed stock. They got lost circulation. They got well kicks. All type of problems happen actually during drilling this well. And again, they had to actually sidetrack the well 3 times, as you can see. And I put actually some numbers here just to convert this problem to dollars. For example, for them to sidetrack this section of the well and reach the depth that they were in it before. So it cost them about 6.7 million US dollar and about 25 days. And for the second time, when they had to do it, it cost them 3.7 million and 15 days, right? There's a lot of money and a lot of basically time wasted on the project. So what happened? For the next well, this company did geomechanical study and they got mud-weight window, right, based on geomechanics. And based on that study, apart from optimizing the mud design for different section of the basically well, we also changed the casing design from the original, this black casing design, to this blue line here. You see some of the casing, we push them deeper, some of them actually put them in different depth. And as you can see, the next well they drilled using the wellbore stability model, they even saved 5 days compared with the plan, right? I don't claim that is always the case. This is one of the basically ideal cases that I was involved. But I mean, even if we save 5 days from this 90 days, 50 days of delay, is a lot of money, right? So this is how geomechanics basically contribute to drilling and save money for companies on the drilling operations. This is a very actually interesting example of a well that was actually decided to be no drill. It means they decided that they cannot drill it. So this is the mud weight window that you see here. So we have the collapse gradient, we have the fracture gradient, and as you see in this section, even with this crazy casing design, they use 1, 2, 3, 4, 5, 6, 7 casing and 1 lining. And they got to the point that even with this design, they cannot drill into this section, right? So they came to geomechanics again and asked, I mean, if we can do anything, right? The decision was that no drilling, we cannot drill this well. So looking at the wellbore stability model, the only solution that we found was that if we change the trajectory of the well in this section from vertical to a deviated well, because as you know, because of the S-stress orientation, the drilling is very, very dependent on the S-stress orientation, right? So it means changing the well trajectory should change the mud weight window. And this is what we did. We changed this vertical well to this trajectory. So basically in that section, we went for a 45-degree well, and we went back to of course, to vertical, not to miss the reservoir. And you see what happened to the mud weight window. Now we have the widest, basically, part of the mud weight window exactly in this interval, which seemed to be, non-drillable. And this is type of, contribution or magic of geomechanics in challenging, drilling projects that sometimes people deem them as like impossible. So one of the outputs of geomechanics, apart from the mud weight window, are these polar plots. And these polar plots are for certain depth or formations. And they are basically color-coded to different parameters. For example, this polar plot on the left is color-coded to the collapse gradient. It shows that how much minimum mud weight you need to drill a well in different trajectories. For example, if I want to drill a vertical well, it's telling me that I need at least 14 ppg of mud weight, right? How if I want to drill horizontally here, kind of the same. But if I want to drill horizontal toward this orientation, 120-degree azimuth, now I need 8.7. It means drilling in this orientation is much basic, not easier, but much safer than these orientations, right? And we can have the same thing for frag gradient, and kind of in each depth we know what the mud weight window would be, right? Now, so usually operators use this type of plots to optimize their drilling orientation in cases that their trajectory is not really solid and they cannot change it, right? If it's flexible, then these are very informative plots to basically optimize the drilling trajectory. Now, this is a project that we got involved in Malaysia a while ago. And the case is that there's a reservoir in a mountainous area, and they were drilling actually from different locations at different orientations to the reservoir, and operators wanted to actually produce from this reservoir as soon as possible. So this is why they were drilling from different actually wells at the same time. So what they did, so I need to mention that this polar plot color codes were put on the wells later, right? Just to show the operators how they were doing, right? So the first well they drilled was a vertical well, and this well actually faced a lot of wellbore stability problems. So the red color wells here are wells that either failed or they were basically encountering severe problems. So later on, when we put the colors on top of the well, we show them why. And the reason was that according to the colors collapse gradient, to drill this well safely, we need some 10 ppg, kind of mud weight pressure, mud pressure to drill this well, while they use only 8.8, right? So this is why they got the problem. The second well they drilled was a deviated well, and based on their bad experience with this well, they increased the mud weight to 9.8, and they drilled it successfully. But now we can see what they did. They used 9.8 ppg, but actually, according to geomechanics, they only needed maybe 9 ppg, right? So not bad, but they're kind of overbalanced. So this well was successful. The next deviated well was exactly the same deviation, but different azimuth. They kept the mud weight the same, and they failed, right? So why? Because they needed actually over 10 ppg mud weight, and they didn't provide that. So the next well, they increased the mud weight based on that experience to 10.2, but actually they just needed, something around 9.3, right? So they're overbalanced basically to drill this well. And you know that being overbalanced increased the time and cost required for the stability, for the drilling. So they drilled unsuccessful horizontal well because they used too low mud weight, and then the next horizontal well successful because they were extremely overbalanced, right? So they drilled 6 well without geomechanics, so they almost lost 50% of the wells because they didn't have these colors. And this is again how geomechanics basically can overall help drilling campaigns to basically reduce the cost, they reduce the risk of losing the well, and so on. And now, apart from having these colors, if you're dealing with anisotropic formations, is another story, right? If we have an isotropic formation and an anisotropic formation, the effect of anisotropic formation is really, really huge, and we need to actually include in our models. So just to do a quick comparison, what I did here, I created the a polar plot, color-coded collapse gradient for an isotropic, basically rock, under a specific, stress condition and pore pressure. And this plot is telling that for drilling a vertical well, we need 11.4 ppg of mud weight. For horizontal, we need 9.8 for horizontal in this orientation. 120 is again 11 point something. So I kept everything in this model the same. I just added a set of anisotropy, which are dipping like 25 degree toward southeast, like this. And you see how the colors basically change. Now it is telling me that to drill a vertical well, instead of 11.4, I need only 11.8, so kind of equivalent, right? But to drill a horizontal well, from 9.8, now I need 14.2, a huge difference, right? So what does it mean? It means if I ignore an isotropy in this formation and deliver this model to my client, and they drill a horizontal well in a shale, let's say shale gas, formation, they definitely fail. They never get to the point that they want, right? So one example that we were involved a few years ago was the first shale gas operations in UK. So the shale is called Borehole shale, and it was basically the first planning for horizontal well and hydraulic fracturing in a shale gas basic asset in the UK. So the company drilled 3 offset wells before, and they were planning to drill this S-shaped appraisal well, and then they wanted to find the landing point and drill this horizontal well, right? So what I'm going to show you is the experiences that they had in the offset wells. This is the first well they drilled in 2011, and I don't say they didn't have geomechanical model. They had geomechanical model, but a very wrong one, right? So it's very important to know that geomechanics is very dangerous. If you have a bad geomechanical model, it not only not helping you, but can easily kill your project. So geomechanics is like a knife. You can do a lot of good stuff with it, but you can kill people. So this is very important to find, actually, to work with geomechanics people or advisors or companies that are really, really good in their field. So this well was drilled with a collection of all different type of problems that you might even imagine, right? So it's the biggest collection of problems that I've ever seen in my life. So from losses to wellbore collapse problem to kicks and different type of problems. And the project was extremely delayed, right? The second well they drilled, they're all vertical wells. So again, the problems are less, but is based on learning from the previous well, but it's still a lot of problem and delay in the projects. And the third well, kind of the same, right? So what we did, we redid the geomechanics. We used all the available data, all the learning from these wells, and we created a 1D geomechanical model for that S-shaped well. So apparently, as you can imagine, why these problems happen. First of all, the mud weight design is not correct. Secondly, the casing design might be actually not appropriate. So we optimized these two designs, and this is the experience with the S-shape actually appraisal well. So these are not problems, these are the coring sections. So the only problems they faced was some basic losses within the reservoir, and the image logs show that there are through basically critically stressed fractures in the reservoir, which we didn't see in the previous drilling. So they didn't exist in the other locations. So, and it was good for them because these are the fractures that are going to actually contribute into a stimulation and production from the shale gas, right? So another application of geomechanics, as you have already noticed, is to decide if we should go under balance or not, right? So again, this is a typical requirement for underbalanced drilling. Collapse gradient must be below pore pressure. And this is the result of a study that we did for a field in northern Iraq. The reservoir was a carbonate, quite competent, strong, but above that was a very long siltstone and shaly section, which the model showed that the collapse gradient is quite high. It means the formations are really weak and they need mud weight support. So there's no way to do underbalance in this section while you can go underbalance to some extent in the reservoir. So it was our recommendation to client that if they want to use underbalance, just use it in the reservoir. And they decided not to listen to us. They went ahead and drilled underbalance, and these are the results. These are the cavings that was retrieved from the well, not with mud circulation, but with fishing. They had to fish these big, pieces of rock from downhole. So, and these cases always remind me of this cartoon when you try to help people and they keep rejecting you because they just think they don't have time, right? And I'm sure you guys have faced this type of issues, trying to helping someone unsuccessfully. So going to I think I'm actually going over my time, so let me go a little bit faster, and so we are able to answer some questions. But I don't mind to actually stay more than 1 hour and answer the questions if you would prefer. So in production applications, I would like to start with one application which is really, really interesting and beneficial to the companies which are dealing with fractured reservoir, like in the Middle East, in carbonate, or even in shale gas, where majority of production coming from natural fractures, right? So usually when you ask production engineers, if you have this bunch of fractures, how should we drill to basically get maximum production from these fractures? the answers that you use is that going perpendicular to the biggest set of fractures, or going to the orientation that we get intersected with the maximum number of fractures. So we look at the clusters of the fractures and design the well. So both answers are wrong, because not all of these fractures are conductive or permeable. So there are actually certain sets of fractures which are producing during production. The rest of the fractures are basically non-conductive, or some people call closed or open versus open. In geomechanics, closed open doesn't really have any mechanical sense. We use the term conductive or non-conductive. So why these fractures behave differently? Because if you put each fracture under a stress field that we already defined for geomechanical modeling, so I put a very simple 2D actually graph here, but it can be explained in 3D the same way. So if you basically find the components of the stress field perpendicular and parallel to these fractures, the larger the ratio of the shear stress to normal stress, this fracture is closer to shear, basically, and go to the shear failure mode, right? And shear failure mode creates dilation or create conduits for the fluid to flow. So mechanically, fractures which are, or faults which are active, they are the ones which are permeable. Other fractures, they might be actually permeable due to other, I mean, maybe chemical solutions or other reasons, but mechanically, we consider them basically non-productive, right? So then the larger the tau, in compared with the sigma n, normal stress, the more possibility that the fracture is productive. So the fractures that this ratio is large enough to basically start displacing in shear, in geomechanics we call them critically stressed fractures or optimally oriented fractures, and those are the productive fractures. How we find them? If we have a geomechanical model, and if we have the natural fractures picked up from image log or any other sources, then we can create, we can do a very simple Moore circle analysis. Is a 3D Moore circle basically representation, which all the fractures, stress combination on the fractures can be actually in this area above the small circles and below the big circles. And this line here comes from the failure envelope of the faults or fractures in the region, right? So we can either get this information from a direct shear test in the lab or from geologists in the region. So they might have regional basically information about the frictional coefficient of the faults. So all the fractures which are close to this line or above this line are critically stressed. The rest are basically non-conductive fractures. So then we can transfer this data, this information, to polar plots and separate or color code the closed fractures or impermeable fractures, the black ones, from the productive fractures or conductive fractures. And this way, you can optimize your wellbore trajectory to basically intersect with the maximum number of productive fractures. So it might actually looks a little bit non-reasonable, but during the 20 years of my actually career in geomechanics, I faced several cases that I actually saw this magic and it worked. One of the, so you might ask, I mean, why? Because these fractures are everywhere anyways, right? So when you drill a well, you intersect all these type of fractures. How can you basically saying that, you know, in this orientation, you intersect with more of this one? Or so this simple graph here, cartoon shows what I mean. So imagine I have these red fractures as the basically productive fractures, and this blue one as conductive fractures, right? And I drill a vertical well. This vertical well is intersecting with 1, 2, 3, 4 productive fractures, right? So how if I drill a deviated well like this? It doesn't intersect with any of them. How about this one? This one is intersecting with 1, 2, 3, 4, 5, 6, 7 of them, right? So it's statistics. We are just changing the trajectory of the well to increase the number of the productive or critically stressed fractures. It's what we try to do. So one example from Lake Maracaibo in Venezuela. I worked for Venezuela I was working for them as consulting for about 6 months. And one of the problems that brought to my attention on the first day of working with them was that they typically, around Maracaibo Lake, they drill into a heavy oil, basically sandstone reservoirs, which are about 20,000 meters below the surface. And for the first time, they decided actually to drill to a Cretaceous reservoir, which is about 4,000 meters below the surface, right? And they got good production actually from that well. So they decided to drill more wells and produce from that reservoir as well. So what happened? The second well they drilled, it was dry, no production. And looking at the image logs, the typical way that service companies look at the image log and define if the fractures are open or closed, their study showed that there are a bunch of open fractures in the reservoir, right? But no production. So we look at the wells, both wells, and we did this critically stressed analysis, and we found what the reason is. So the first well that they drilled, so you see these color codes? So the red colors shows that there are more critically stressed fractures in these orientations, right? Compared with the rest, right? So the first well they drilled, they got stuck in the carbonate actually. I don't remember it was the wellbore stability issue or mechanical issue, but they had to sidetrack the well and drill this kind of 20 degree deviated well. And this is the well which was producing. And now you can see why it was producing, because it's very close to the red region, right? The second well was a vertical well. And now you can see it's actually not intersecting with many productive fractures. So it's why it was dry. So I suggested them to drill within this region, and hopefully they get better, results. So, and I left Venezuela after 5-6 years. I just remember this case, and one of my colleagues in Dong Energy in Denmark recommended me to contact them to see what happens to their case. So I contact my colleague there, and they said actually that they drill about 10 wells in this region, and the production was 2 times bigger than this one, the first one. And it kind of proved me that this technique is working, right? This analysis is very effective. So going quickly to the hydraulic fracturing, there are different applications for hydraulic fracturing to enhance well productivity, as you know, to introduce thermal energy, for CO2 sequestration, for engineering, or enhance geothermal systems, to major stress, small size hydraulic fracturing like mini frac, DFIT, LOT. For cutting injection, some companies use fracturing. But as you know, the biggest application in the US specifically is for development of unconventional resources and doing multiple fracking technology. So there are many aspects in hydraulic fracturing, like fluid design, like frac design, the completion design. Geomechanics can contribute into hydraulic fracturing in these basically aspects. It can increase efficiency with identifying frackable intervals. So we need to look at the mechanical property of intervals to see if it's frackable. We can create a fracture or not, right? We can basically, based on the rock properties, we can suggest what type of downhole pressures are needed to create the fractures and keep the fracture size within a certain limit, which is safe to us, right? And then predict orientation of the fractures. Fractures typically, theoretically, go perpendicular to the minimum horizontal stress, but in anisotropic formations or when natural fractures are involved, this will be affected by that, basically rock properties. And we can optimize drilling direction to minimize hydraulic fraction pressure, right? So this is an example of basically naturally fractures getting involved in hydraulic fracture. As you see, the induced fracture get affected by these fractures, and based on their weakness, right, what their friction angle and cohesion is. but the overall orientation of the stimulated zone is still perpendicular to the minimum horizontal stress, right? We can model this with geomechanical software like numerical modeling, and we can basically see which type of fractures get actually involved in the stimulation, and which fractures are very, very basically critical stress-wise far away from the envelope, failure envelope, they cannot be actually involved in the stimulation, right? This is a very important analysis for hydraulic fracturing and finding the real, basically, stimulated volume of the reservoir. So this is another example of basically hydraulic, is the horizontal well, and how the natural fractures get involved in the stimulation, right, based on stress and rock properties. So, and I want to actually conclude my presentation with one case study from Pakistan, where the client was basically testing or appraising a tight carbonates with permeability of 0.01 millidarcy, very low permeability, and 2% porosity. So what they did, they drilled basically an appraisal well, and this well again got wellbore stability problem in the reservoir. They sidetrack it, and in that sidetrack, they did some stimulation, preliminary stimulation to basically get production. The first thing they did was the matrix acidizing, and after that, the production went from 0 to 11 basically. And then after the 100 hours, it dropped to 1.7, which is not really an economic, production. Then they tried a proppant fracturing using a new technology provided or introduced by one of the major service companies. It's called P.A.S.S. I don't use the commercial name, but it's kind of P.A.S.S. Fracturing. And the idea is to basically reduce the amount of the volume of proppant needed, just to economically help the operator to save some money, and also keep some basically conduits open for oil and gas to flow better in the fracture, right? After this, they lost even this 1.7, low production, so there was no flow. And then again, they did acid fracturing, very limited acid fracturing stimulation, and they gained kind of the same production they had after acidizing. So their plan was to drill a horizontal well and do again some testing, simulation testing in that, but they decided not to use that service company. So they came to us and asked us to do a geomechanical modeling and fracture design. So the objective of the study was to develop 3D geomechanical modeling for the field, optimize new well trajectory and packer placement for the horizontal well, and providing recommendation regarding optimal type of stimulation and detailed pumping schedule, right? So this is kind of a 3D geomechanical model that we created for the field. These are the vertical and basically the sidetrack that they already had. And this is the horizontal well that they were planning to drill. So we came up with the present day stress regime and the rock property model in 3D. And this is basically the site view of the well. So it's not horizontal, it's semi-horizontal. As you see there, these are the planned sections we designed for 10 stage fracturing, starting from basically the toe to the heel, and then we optimize the location of the injector. These are basically open hole fracturing. Is not there's no case and perforation involved here, but there were two main limitations for us. One was the cap rock here, which is a shale, and of course, I mean, in this case, the minimum stress difference between the two formations was not really large to call it safe cap rock. So we have to be very careful when we frac close to the cap rock. And down there, actually, geologists interpreted a water level or a spill point, to be actually at this section. It was about, if I remember right, was 16 meters actually far from the well. So we had to limit our design to not to frack into the cap rock and not to frack into this water zone. Otherwise, we would be in trouble, right? So we ran actually several different frac design, but using different, proppant, fluids, gels, and stuff. And we even tried acidizing, acid fracking, in order to basically find the top 5 optimized design for this setup. And then we took these top designs to 3D hydraulic fracturing modeling. So because we believe that the typical softwares in the market that use classical frac design, they're good for comparison, right? To test different designs, but they don't really give you the size and the orientation and tortuosity of the fracture close to what happens in the nature. Actually, they are not really accurate, right? So if we want to get better estimation of the geometry of the fracture, we have to go with 3D geomechanical models and 3D hydraulic fracturing modeling. So based on this type of modeling, which shows how the fracture grow, propagate after each stage of pumping, and how far the proppants are basically going to the fractures. So these color fractures are color coded to the width of the fracture, right? So based on this type of comprehensive analysis that we did, we end up with these designs for the well. For zone 1, which was close to the water level, we didn't recommend fracturing. We recommend matrix acidizing because it was very risky actually. Zone 2 to 4, we suggested some kind of acid fracturing, but we call it close fracturing acidizing. First, we frac formation without proppant, and then we acidize that fracture. And it helps us actually to have a better control on the size of the fracture, but it creates much larger fracture in compare with the acidizing, with acid fracturing, right? So zone 4 to 8, we went for large size fracturing using the proppant fracking with a specific type of fluid and gel. And 9 to 10, which was close to the cap rock, we went for medium size fracturing using clear fracking and so on, right? So fracturing operation was completed actually back in 2017, and right now some of the wells in the reservoir are producing 30 actually million cubic foot per day. So it's a kind of good production for that low permeability formation. So, and the last slide, if you are interested in hearing more about basically typical mistakes that we are doing in the industry with respect to wellbore stability, I'm giving a SPA distinguished lecture, basically planned for 2020 and 2021. It will be probably delayed or changing the schedule because of this COVID-19 problem. But if you are interested, just keep your eyes open for announcement from SPA to basically discuss more about the wellbore stability issues. Thank you very much. I'm over my time, and I'm open to answer questions. Sorry about the length of the presentation.
Thank you so much, Hamid, for this nice presentation. Let's now take a few questions. Hamid, one of the persons asking says, share your insight about the role of geomechanical approach 3D in enhanced oil recovery.
Yes, it's one of the applications that was actually underestimated until a few years ago, but currently almost all the EOR projects need to have, basically geomechanical study before it. And the reason is that when we inject into the reservoir, right, we are changing not only the stress condition, not only we are changing the pore pressure, we are changing the rock properties, the fractures and fault properties. And this injection might actually create reactivation of the faults and fractures and create microseismic events which are above the standard limits and might actually create problems to our projects, right? So any type of EOR which is involved in injection, we need to do geomechanics to basically be able to predict the reaction of the reservoir rock and fractures faults to the injection, right? It is applicable to CO2 sequestration, is applicable to any type of project that we do injection into a rock formation.
All right, the next question is asked about how geomechanics help in designing polymer-based fluid and flooding design.
So I didn't get the question, Salah, sorry.
How geomechanics help in polymer-based fluid design and flooding design?
Yeah. This topic is more reservoir engineering and how this type of fluid basically physically and chemically react to the rock. But from geomechanical point of view, we still look at the it's kind of hydraulic fracturing, right? We can see the effect of viscosity of the fluid on the fracturing. We can also look at the viscosity of the fluid you're injecting and density pressure and see how this basically, and we can optimize the type of fluid to minimize the reactivation of fault and fractures, right? But from reservoir aspects of it, how much it increased the production, that's not geomechanics, right?
All right, so the next question, have you got any global statistics about the contribution of geomechanics in drilling?
Unfortunately, there's no such statistics. I have several statistics from different locations, like North Sea, like Gulf of Mexico, like what I presented. And most of these statistics are from 90s for some reason. One of the reasons that we don't see new statistics is that a lot of information are confidential. Operators don't share this type of information anymore. But there are some papers that individually look at the, some drilling operations and discuss the effect of geomechanics on saving money and time for that specific projects. So I'm really interested if you guys are connected to a company or working for a company that has this type of statistics, please share if you can.
All right. What are the main challenges associated with the calibration data?
Yeah, that's a good question. Calibration overall is a challenge for geomechanics because typically we're asking for data that drillers or petrophysicists, they don't need those data. Like one of the key data to calibrate the minimum horizontal stress profile is the extended leak-off test. Drillers hate that, right? One of my biggest challenges during my career has been fighting or not fighting, arguing with drillers to get to make them do extended leak-off tests, right? Rock mechanics testing, right? This is usually time-consuming, expensive, and only geomechanics use it. It doesn't have any use for petrophysics or reservoir engineers, although it's important for them, right? The result of our study goes to them as well. So again, is challenging to convince operators to spend this money. Although many operators right now, they are totally educated on this data, and then they acquire that. And like image logs is a key log for us that some other people don't care about it, but in geomechanics is extremely important. But again, expensive to acquire that. But the good thing is that with having advanced knowledge and tools like data science right now and signal processing methodologies coming from other disciplines, we are able to actually create synthetic calibration data, what we are doing currently in Petrolern. We are developing actually new methodologies to estimate the stresses and rock properties from data which doesn't require actually a lot of money to acquire, right? Very, very simple type of data that can be acquired easily anywhere. And develop methodologies to basically digitalize our calibration using drilling incidents and easy acquired data. Yeah, but calibration is always a challenge for geomechanics.
So let's take two more questions. The first one is, can you please explain wellbore instability issue in salt formation and the reason for using high pressure mud weight in these formations?
Yeah, the problem with salt, saturated salt, is that is a plastic material. right? It's like dough, right? You make bread with it. So how you drill into that? As soon as you drill, the wellbore start closing, right? And honestly, the mud pressure can partially solve the problem. First of all, you are not allowed to use any basically water-based mud, because it will it has I mean, solve the basically the salt and create bigger problems. So the mud has to be oil-based. The pressure should be optimized to avoid, you know, the mechanism for failure here is called squeezing. Squeezing is deformation without changing the volume of the material. It is different from swelling that happens in shale, right? So practically the easiest or the simplest way to drill is to drill as quick as possible with an optimized basically mud, and just drill through it as fast as possible, right? Currently we have technologies like drilling with casing that can help with that, or basically expandables that can isolate that sections from other part of the formations if you have to expose the interval in a longer time. So yeah, technology basically is the key to solving this type of problems.
How can we avoid induced seismicity? Do you have information on Poland induced seismicity that can be shared?
Yeah, so part of this question's answer goes back to the frac design. If you're talking about fracturing, I assume, or it is related to the EOR as well. So part of it goes back to our designs to optimize our frac design, the fluid we use, the stages, and the pressure we apply, which basically goes back to our understanding of geomechanical properties of the reservoir, right? If we don't have right information about the fractures, about the rock properties, basically it's impossible to even stop huge, you know, microseismic events. But at the end of the day, I should confess that even we have a very good geomechanical model, we have a very good you know, frac design, we cannot claim that we can stop microseismics fully. It is impossible, right? Because we cannot really fully 100% understand the nature. Like, you know, we did a good job for UK shale gas. We basically spent a lot of time to understand the geomechanics, the fractures. But I mean, and I don't know if you are aware of or not, but the maximum allowable microseismic event in the UK is 0.8 magnitude, which is almost nothing. So all our design was based on that, to keep the microseismic below this level. But at the end of the day, they had events of magnitude of 1.2, 1.4, as because, I mean, it goes out of the control sometimes there.
Thank you again, Hamid, and thank you everyone for joining us today. Please make sure you follow us on LinkedIn to receive updated information about the upcoming talks. With that, you all have a good one. Bye.
Thank you, Hamid. Thank you.
You're welcome, Aziz. Thank you all. Sorry for the long times.
No, it was nice.
Thank you, Hamid. Thank you.
Thank you, everyone.